Picture a massive muscle car tearing off a starting line, fighting with thousands of pounds of weight just to push itself forward. Compare that to a standard sport bike at a traffic light, lifting its front tire into the air with a simple flick of the wrist. For a car to pull its nose off the asphalt, it takes an extreme, specialized environment. It requires immense horsepower, massive rear slicks, and incredible track grip to generate enough force to launch those front wheels into the air. Motorcycles require a fraction of that power to achieve flight. A casual twist of the throttle on a relatively light machine is all it takes to send the nose skyward. To figure out how a rider actually survives this balancing act, we need to hit pause. By freezing a 10-second wheelie in midair, we can forensically dissect the invisible forces making it happen. What looks like a moment of reckless chaos is actually a highly precise operation. The rider is actively managing a complex physics equation in real time, balancing extreme power against the downward pull of gravity. Let's rewind the timeline to the very first millisecond of the launch, right as the rider's hand aggressively twists the throttle. Instantly, a massive burst of rotational force is sent straight to the back wheel. The rubber bites into the asphalt and compresses as it attempts to violently drive the bike forward. As the engine pushes the frame forward, the total weight of the vehicle and rider instantaneously shifts backward toward the rear axle. This transfer pushes the rear tire hard into the pavement, expanding its contact patch, while the front tire's load rapidly drops to zero. If the machine's mass didn't aggressively transfer to the rear like this, the engine would just spin the back tire into smoke, and the front wheel would stay firmly anchored to the ground. Now, let's advance the clock just a fraction of a second, right to the exact moment the front wheel breaks contact with the pavement. The rear wheel has essentially locked onto the road and become a fixed pivot point. As the engine spins the rear tire forward, physics pushes the entire body of the bike backward and upward. It is a process known as torque-induced rotation. But not all bikes want to rotate. Take a look at this cruiser motorcycle. Its long, heavy frame and stretched wheelbase keep the center of gravity spread far out toward the front, naturally resisting any of that upward lift. A modern sport bike is built entirely differently. Its wheelbase is ultra-short, packing the engine, the rider, and the center of gravity into a tight compressed space much closer to the rear wheel. Because the weight is already concentrated near that rear pivot point, the engine torque easily overpowers the front end. The sport bike's geometry is exactly what turns forward thrust into upward flight. Let's unfreeze time again. We watch the bike's nose rise high into the air and hit pause right as it reaches its absolute maximum height. The rider is now sitting directly in the balance point. This is a razor-thin angle where the upward thrust generated by the engine perfectly neutralizes the downward pull of gravity. To stay in this zone, the rider makes microscopic adjustments to the throttle. If they roll off the gas, the front end drops. Feed it too much power, the bike flips over backward. There is a vital mechanical failsafe in play here too. The rider keeps their right foot hovering directly over the rear brake pedal. If the bike rotates too far back, a quick tap on that brake immediately kills the momentum and slams the nose back down. Holding that front tire in the air requires constant, rapid inputs. It is a frantic physical dialogue between human reflexes, engine torque, and gravity. Returning the footage to normal speed, we see the rider seamlessly carry this high-angle wheelie all the way down the city block. In recent years, humans are no longer the only ones calculating these split-second equations to keep the rubber side down. On this digital wireframe, internal measurement units track pitch angle, wheel speed, and rotation hundreds of times per second. If the computer detects the nose rising too fast, algorithms automatically intervene. The system cuts engine power, preventing a flip faster than a human reacts. The mechanics of the machine want to push it over backward, while gravity desperately wants to pull it down. Whether it is balanced by the practiced foot of a daredevil or the invisible algorithm of a microchip, a wheelie remains the ultimate demonstration of dynamic equilibrium and controlled power.